So I'm going to start with a little light review as kind of getting back started, because some of the topics that are kind of foundational to what we're doing in Chapter 7 are things from first semester or even all the way back into our geometry class, and that was a long time ago for a lot of us. So let's take a moment, kind of review some of those topics, and then we'll kind of extend from there to start Chapter 7. So the main thing that we're going to be talking about here in Chapter 7 is solving triangles. And we've already talked about a narrow slice of this topic in your geometry class, where we talked about solving right triangles. When we talk about solving a triangle, what do we mean? We want to find all the missing side lengths and angle measures. So where you're given some of the information, but not all of it. We want to find the rest of that missing information. To do this, what tools do we have that we can use to solve right triangles? Anybody? Things that we can use with a right triangle? Think back to your geometry class. Great. What else? Excellent, yes. Remember, Sohcahtoa is an acronym that describes the relationship of side lengths, or ratio of side lengths, to the three trig functions, sine, cosine, and tangent, right? Everybody remembers, you don't have to write that stuff down, right? We're good? Okay. And then the one other one that I would say that would be particularly useful isn't limited to specifically right triangles, but it's that the sum of the interior angles of a triangle is 180 degrees. Everybody kind of, that stuff's all relatively familiar. Let's run through a couple of quick examples here. So there's two basic situations that we can be in when we're solving a right triangle. One situation is where you're given like an angle measure and a side length. And the other situation where you'll be given two side lengths. We'll do one example of each of these two situations. Okay with that? All right. Okay. So in this first situation, you're given an angle and a side length. So there's three pieces that we still need to find. We need to find angle B, we need to find side AC and side AB. Cool? What's the easiest thing to find straight from the get-go? Angle B. How do you do it? Great. Yeah, so like 180 minus 90 minus 43. So that's 47. And again, if you have any penmanship questions about like what the symbol is or the number or anything like the letters, you can't read my writing, please holler at me. I acknowledge that my penmanship is less than spectacular at times, so Don't be shy about that if they're like, yeah, I can't read whatever you wrote there. I might act annoyed, but it's just because I'm frustrated that my penmanship is terrible. It's internally directed, even if it appears to be directed at you. I promise it's not. It's just me being frustrated with myself. Okay, next up, we can find A, B, or AC. Note that the order in which we solve these things does not matter. So just because we started with angle B doesn't mean you have to start that way. It's just so trivially easy. That's what I'd like to do. But you certainly don't need to start with that. Which side do you want to solve for first, AC or AB? It doesn't matter. Let's say we pick AC then. Okay. The next thing we're going to need to do is choose the angle that we want to use to solve for side AC. We know the 43-degree angle and we need the 47-degree angle. You can pick either one of the acute angles. You cannot use the right angle. Okay? For the sake of argument, let's say we pick the 43. Relative to that 43-degree angle, AC is opposite, adjacent, or hypotenuse. Adjacent. And the 10, the side that we know, is opposite, adjacent, or hypotenuse. Opposite. So, which trig function should we use that uses opposite and adjacent? Tangent. So we'd say tan 43 is equal to opposite over adjacent. So now we just need to solve for AC. To solve for AC, we got to get that AC out of the denominator. How do I do that? Good. Multiply both sides by AC. And then we have to divide by tan 43. Very good. And then it's calculator time. What do I have to be careful about with my calculator before I type this in? Yeah, we have to make sure we're in the correct mode. What mode should my calculator be in, radians or degrees? Degrees. How do I know that? The angle's in degrees, right? So I am in degrees. So we'll just do 10 divided by tan 43. And we got 1072. Everybody happy there? Okay. How do you want to solve for AB now? We could use the Pythagorean Theorem, absolutely. So what equation would I write then? Yeah, very good. So the thing that we have to make sure that we're being careful about with the Pythagorean Theorem is the hypotenuse is the piece by itself. I know I shouldn't have to say that we're all like no doi, but people make that mistake all the time when we're going fast and not being careful. So I'm just going to say it now. So to get the AB by itself, I got to get rid of the squared, so we'll just square root both sides. Note that 10.72 squared plus 10 squared, you can't make 20.72 squared. Can't add those together because of the order operations. You'd have to square it first before you add. Similarly, you can't distribute the square root and say, oh, the square root of 10.72 squared plus 10 squared is just 10.72 plus 10. Nope. Square roots don't distribute. So I'm just going to type this into my calculator just like it appears. So square root. And I'm going to use the answer command rather than typing out the 1072. And I get 1466. Everybody feel good there? One little quick check that I can do at the end. It doesn't guarantee I have the correct answers, but often will catch a significant mistake. is that I know that the biggest side has to be across from the biggest angle, the middle side has to be across from the middle angle, and the smallest side has to be across from the smallest angle. If I look at this, my smallest angle is 43 is across from 10. That's the smallest side. That looks good. 47 is my middle angle. That's across from 1072. That's the middle side. That looks good. My biggest angle is the 90 degrees. That's across from the hypotenuse to 14.66. That's the biggest. That looks good. Okay? Not a guarantee that you've got it correct if those things match up, but probably, you know. Unless you did something goofy and just like transposed a decimal point or something. Okay. The other situation is where we have something like this, where you're given two side lengths and we want to solve the right triangle. Again, it doesn't matter which piece you want to solve for first, the side or the two angles, although I think that one of them, it's pretty obvious what to do right away. Which one does it appear to be the easiest to solve for square away? BC. What would you do? Pythagorean theorem. So what equation would I write? BC squared plus 10 squared equals 17 squared. Again, got to be careful that the hypotenuse is the piece by itself, right? Okay, so we'll subtract 10 squared from both sides and then square root both sides. Again, holler at me if I'm going too fast or I skipped some steps and you don't see what I did, or if you think I made a mistake or anything like that. All that kind of stuff happens. I'm not infallible, and sometimes I do get excited and just start rocking and rolling, and if I'm leaving you behind, that's not my intention. So 1375. So far, so good. Okay. Let's pick an angle to solve for next. Does it matter which angle I pick? No. Let's say for the sake of argument, we're going to pick angle A. So relative to angle A, the two sides I know, the side that's 10 is opposite, adjacent, or hypotenuse? Adjacent. And the side 17 is opposite, adjacent, or hypotenuse? Hypotenuse. So which trig function should I use for adjacent hypotenuse? Cosine. So we'll say cosine of A is equal to adjacent over hypotenuse. Everybody so far so good? Okay, we have to solve this equation for A. How do I get the A by itself? I got to get rid of that cosine that's in front of it. Well, cosine's an operation, so you can't divide by an operation. That'd be like saying, oh, I'm going to, get rid of this square root symbol by dividing by square root symbol. Sydney? Yeah, so we're going to use cosine inverse on both sides. Exactly right. So remember that the inverse trig functions will return an angle measure, right? So cosine inverse cancels cosine. So you're left with A is equal to cosine inverse of 10 over 17. And remember that, again, these inverse trig functions give you back an angle measure, right? They take a ratio of side lengths and they return an angle measure. So that makes sense since A is an angle. So I have 5397. So far, so good. Now angle B. What do I want to do there? Maddie? Exactly. Yeah, that's the easiest way to do it. I mean, obviously, you could do what we just did all over again, but like, who wants to do that when you can just do some addition and subtraction, you know what I mean? Good. Fiddlesticks, I pressed the wrong button there, didn't I? There we go. 3603. Cool. Any questions on what we've done here? Pretty straightforward, right? Okay. It should be, because this was all geometry topic. So the question that we're left with now is, what about non-right triangles? Since they're non-right triangles, do we have the Pythagorean theorem to use? Since they're non-right triangles, do we have Sohcahtoa? Nope. Oh, Boise, what do we do? Well, the answer is going to be what we develop in Chapter 7. Okay? So in Chapter 7, we're going to look at two tools. The first one is the law of cosine, or law of sines, excuse me. So what the law of sines says is, for any triangle, right or not right triangle, the following holds. So let's kind of show why this formula is true. Okay, right? It's one thing to write it down and say, okay, believe me. It's another to like, why does that work? What? So here's the trick of how or where this formula comes from. Sydney.
What's in between sine A over sine A over A?
Oh, these are all equal signs. So let's show you where this formula comes from. Sound good? All right. So what we're going to do is we're just going to pick one of these angles. Let's say angle B. And I'm going to draw a perpendicular line from angle B to that opposite side. I'm going to label that side as, or that new perpendicular line as H. For height, because it's the height of the triangle. Everybody's okay with that? So if I look, I have a right triangle here. Yes? So I could say that sine of A is equal to opposite over hypotenuse. And I have a right triangle here. And I can do the same thing. I can say sine of C is equal to opposite over hypotenuse. I can then get these two equations both equal to h. So the first equation, I multiply both sides by c. And the second equation, I multiply both sides by a. Since they're now both equal to h, I can set them equal to each other. And then I can divide both sides by AC. Doing that, I'm left on the left with sine A over A, and on the right, sine C over C. Everybody okay there? So that gives us like this part of the law of sines. Then all I need to do is repeat that same process, drawing the perpendicular from either angle A or angle C, and I'll get another part, and then I can transitive property it all together to get this. We've done the hard part here, though. I'm not going to repeat the same steps with different letters, though. Is that cool? But that's all this is doing. It's just basically saying, oh, okay, if I divide this up into two right triangles, then I can do the following. Okie dokie. Okay. The other tool that we have is the law of cosines. So for the law of cosines, I can say that a squared is equal to b squared plus c squared minus 2bc times cosine angle A. Or I can say b squared is equal to a squared plus c squared minus 2ac cosine of angle B. Or I can say that c squared is equal to a squared plus b squared minus 2ab cosine angle C. Notice that this is basically the same formula 3 times in a row, right? All we've done doing is like substituting letters. The way that I remember this is if I'm looking for side A, I need angle A, and then the legs fill up everything else, right? The piece that's by itself is the piece that I need the angle for. And then the legs fill everything else in. Okay, so I guess we don't derive that, that's fine. We'll just talk about it for a second. So if I look at the law of cosines here, what does it kind of look like? Looks a little like the Pythagorean theorem, right? It just has like this extra correction factor at the end because it's not a right triangle that we're working with. If we are using a right triangle, then that cosine is going to be 90 degrees at the end, which is 0, which just drops that whole correction factor off at the end, and you're just left with the Pythagorean theorem. So, cool. Okay. The next question you should have is like, okay, so we have these two tools. When we're dealt with a right triangle, it was really obvious when I wanted to use Sohcahtoa and when I wanted to use the Pythagorean theorem. That was super obvious, right? Here, when would I want to use law of cosines and when would I want to use law of sines? Well, the easiest way to remember this is we're going to use that same notation that we did when we talked about similar and congruent triangles back in geometry. So you remember when we talked about similar and congruent triangles in geometry, we had these like 3-letter abbreviations for the different situations, right? Like you had side, angle, side, and angle, angle, side, and all those things, right? Those are going to be the same kind of criteria that we're going to use to decide whether we should be using law of sines or law of cosines. So for the law of cosines, we'll do that if we have a side, angle, side situation or a side, side, side situation. I'm going to put a little asterisk on the side, side, side situation, though, because there's a little bit more to it than just the law of cosines. We have to be a little bit careful there because something weird can happen. And in the law of sine situation, we'll do that if we have angle, side, angle, 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 side, and then we'll do that also if we have a side, side, angle situation. I'm going to put an asterisk there because, again, we have to be careful because some weird things can happen. This one in particular should stick out to you, though, because if you think back to your geometry course, was there a side, side, angle congruence theorem? No, there is not. And the reason there is not is because it's possible, if you pick the right 2 side lengths and angle measure, that you could construct 2 different triangles that have that same side length and that have congruent side lengths and angle measures. They're 2 distinct triangles. Okay? So that's in particular, we have to be very careful in this side-side angle situation because there's some times where we can get 1 answer and there's sometimes we can get 2 answers. And I think, well, even 0 answers is possible in a like degenerate's case situation. But so we have to be very careful there in the side-side angle situation. Okay. How much more time do I have here before I start getting into examples? You know what I mean? I don't want to get like halfway into something, then be like, oh, it's time to go. Oh, we still have 15 minutes. Okay. We can do an example in 15 minutes. All right. Okay. So let's say we want to find or solve the triangle where one angle is 32 degrees, another angle is 73 degrees, and the side C is 13 inches. So the first thing that I'd want to do here is I'd want to draw and label a picture. And when we draw and label our picture, I don't care a hill of beans about the scale, but the labeling that I'm doing definitely matters. So I'm going to label my 3 angles as A, B, and C. And now I'm going to label my side lengths so that they correspond to my angles. So the side that's opposite angle A, I need to label as side A. The side that's opposite angle B, I need to label as side B. And the side that's opposite angle C, I have to label as side C. If you do not label your triangle correctly, you will not get the right answers. Okay, critically important that you're carefully labeling your triangle so that the side opposite the angle, the label matches the angle label. Okay? Got to make sure we're doing that correctly, or all of these equations are going to just blow up in your face and you're going to get like bonkers answers. Okay? All right. So let's see. Angle A is 32 degrees. Angle B is 73 degrees. And angle C is 13 inches. Which situation are we in? Incorrect. This is angle side angle. Why? What is the difference between angle angle side and angle side angle? Angle side angle, the side is in between the two angles, right? So that side in angle side angle is an arm on both angle A and angle B, right? Everybody agree? If this was angle side angle or angle angle side, you'd either be given side A or side C. Where angle or side A is not a part of angle A, or side B was not a part of angle B. Everybody's okay with that? We can see the difference. Important that you're able to see the difference between those, right? Particularly when choosing between side angle and side angle side. Right? That's the one where it matters for sure if you screw that up, because one tells you to do law of sines, the other says law of cosines. Okay. So we need to find angle C, we need to find side A, and we need to find side B. What should I do first here? Angle C. Very good. So 180 minus 73 minus 32 comes up with 75 degrees. Now I know I'm going to be using the law of sines, right? Because we have an angle side angle situation. So if I look at the law of sines, which ratio do I know completely? Do I know sine A over A, sine B over B, or sine C over C? I know sine C over C. So that's the piece I'm going to be using. Everybody okay with that? And then I'm just going to pick. Let's solve for side A first. So I can say then I have sine of angle A, which is 32, over side A. And now I just have to solve for side A. So I'm going to cross multiply. And then divide both sides by sine 75. And then it's calculator time. I'm going to use the fraction function on my calculator, so I don't have to worry too much about the parentheses, and I can just type it in exactly like it looks like on my sheet of paper. So I get 7.13. How do I solve for side B? Same thing, right? Note that what I can't do here is the Pythagorean Theorem. It's tempting to want to do that, right? Oh, I have two sides, solve for the third, Pythagorean Theorem. Why not? It's not a right triangle. And it's calculator time again. So 1287 there. And then let's do a quick little check here. Is the smallest side opposite the smallest angle? Yes. Is the middle side opposite the middle angle? Yes. Is the smallest side or biggest side opposite the biggest angle? Yes. Does this look good then? Probably, right? Not a guarantee that that's the case, but like if that what we just said isn't true, you're guaranteed you have a mistake. This doesn't guarantee it's correct, but if there's a definite mistake, it can definitely catch a mistake, right? It doesn't guarantee to catch all the mistakes, but it can 100% tell you it's not right. I can't tell you if it's 100% right, but it can tell you that that's definitely not right if that's untrue, which is better than nothing. We're going to stop here because, quite frankly, I don't want to get too deep into this before the bell rings and have to pick up later. But this feels good.